Thanks for coming, everybody. Today I'm going to give you an update on my work, my PhD work on intelligent adaptive underwater sensor networks. I'm working with Hugh and Professor Karen Jenny, Dr. Karen Jenny. The outline of the presentation involves, I'm going to introduce you to the problem and explain what's the motivation. Then I'm going to put my research in context with what have been done so far and explain my new idea or how I want to approach the problem. And then I'm going to finish with listing my achievements and plan for my future work for the rest of the PhD. The problem I'm working on is naval mines. It is one obvious problem is that it causes very expensive damage. Here you can see on this graph how some simple and old mine design can cause substantial monetary damage to ships. And it's old mines from the Second World War that are causing problems, but also the new mines that are designed, they have quite intelligent actuators, and they can choose their target based on the signatures they detect. So this brings the issue with what are the current means that we have for countering this problem. One typical way is minesweeping, which is to imitate signatures of ships, and this causes the mines to trigger. However, as I said, modern designs can actually choose their target, so this is not enough. Another way is to use mine hunting, which is normally a big ship that is towing imaging sonar, and you're scanning a large area of space and then disposing of the mine with an ROV. But an obvious issue with this is that you cannot look at the mine from all angles or from close proximity. And as you can see, this picture, it's a bottom mine which has some growth on top of it, so they can become quite invisible. So from this point of view, we can do better by using autonomous vehicles linked together in underwater sensor networks. There are other applications except mine countermeasures. For example, for scientific applications, in case you want to collect some samples from different points in space, you can launch multiple vehicles. This is a picture that I took in Southampton, the National Oceanography Center. Those are their vehicles. They can reach up to 6,000 meters depth. This is the SeaCat. It's a vehicle that is built by my sponsors in Bremen, and it can be used for mine countermeasures. Another common application for underwater sensor networks is search and rescue. Some common problems that such systems solve is that they can cover large areas where a single platform might not be able to do. In the case of mine countermeasures, the personnel safety is quite important, so when you're having autonomous platforms, you can keep the personnel safe on the ground. And the third thing is that potentially with the development of such systems, they can bring time and cost efficiency. So having said that, my work is focusing on managing the resources in such ad hoc underwater sensor networks, and I'm focusing on mine countermeasure applications. So the three main issues that I'm looking at are communications, since underwater communications are quite an issue. The operation configuration, which is limited by the operations in mine countermeasure scenarios, and also the allocation of tasks for the vehicles or the resources that you have in the network in general. Right. The major issue for even establishing a network underwater is the communications. one big difference between terrestrial communications, the way that we are used to using such network, is that radio frequency doesn't propagate well underwater. You can have signals that are transmissions up to a few meters, which excludes medium to long ranges between vehicles. Another way is using optics. However, in shallow water, where most mine countermeasure applications are located, because of the turbulence of the water, you have a lot of most of the signal is dispersed, so this is not feasible at the moment. Again, you have only a few meters of distance that you can transmit. So the only feasible option for long-range communication is acoustics, and there are some challenges related to them in terms of wireless communications. First of all, the obvious difference is that the speed, if you compare it to an RF signal on ground, which is traveling with the speed of light, the acoustic signal underwater is traveling with 1,500 meters per second, which is about 100,000 times slower. And also this brings different frequency for the signal, which limits severely the bandwidth and maximum data rate which you can achieve, which is in the kilobits, but often in bits per second. And this is a small example that hopefully will give you a better idea. If we imagine an area that has been scanned that's 100 meters by 100 meters, and you can imagine this is a vehicle that's going, that's traveling in the middle, and it has imaging sonar on scanning on both sides, with a resolution around 10 centimeters, and it can cover this area for around 1 minute. The volume of that it's going to generate with the sonar is in the range of tens of gigabytes. And if you compare it to the kilobytes, which is the best case scenario that you can get, it's impossible to get through raw data like this. Alright, then I have looked into some examples of networks that have already been tested in real trials. There are not that many examples, actually. One of the early experiments that involves autonomous underwater vehicles for mine countermeasures is from around 10 years ago, and it involves the typical for mine countermeasure operations route that is lawnmower pattern, where in this paper they have one vehicle that is searching the area and another vehicle that is going after those crosses to look at the target from closer proximity. But in this paper, although they're mentioning autonomous operation, it's not mentioned at all that the vehicles were off of the operator control, so they're probably just controlled by the operator without actually having communication between them. Another example, which is covering the more the networking part in an ad hoc network with static nodes. This example is good to see what's happening when you're trying to route the messages. If you want to hop a message between nodes. And in this table, you can see the latency in seconds per hop. This is just to send one packet between node 1 to node 5. So the big latency in the beginning is because first to find the route, it takes quite a long time, and then it's still quite a big latency to queue all the packets. And this is only possible with static nodes. When the nodes start moving, it's going to take even long time. And just to give you a comparison with RF signals that are rerouted, the rerouting packets, the delay is sub-seconds, while in underwater acoustic networks it's 10 to 100 seconds. A very recent example of a network that has been deployed is Grex. Their aim was to explore hydro vents. So they wanted multiple vehicles that are traveling information, but what they managed to achieve was to deploy two vehicles that were quite different between each other, and all they could, their results showed that it's very difficult to scale up a system to include more vehicles, and one staggering result for me was that only 60% of of the messages that were sending between the vehicles were actually successful. 40% of the messages were lost. More is another example, which is still, the trials are still ongoing. It's another scientific project that is aiming at imaging structures that are normally hard to image, like vertical structures and coral reefs. And what's interesting about this formation is that instead of using one big vehicle with a lot of expensive sensors, they have divided the sensors into different vehicles. So you can send the camera vehicle to explore a certain angle and another camera vehicle from a different angle. So this is more or less what is currently the state of underwater networks. And for my project, I have been looking at the idea that can be easily explained by the Boy Scouts analogy from sensors as robots from Mike Wicks. So if you imagine a group of Boy Scouts that have the task of cleaning a park area, and tasks can easily change on the fly. And because certain areas can have more garbage than others could be almost clean. So they communicate between each other, make decisions, and in this case, they're independent, autonomous units that are resolving the situation in cognitive operation. And if you apply this example to an underwater sensor network, and if you imagine that the acoustic channel is providing, introduces noise to the system, and again with the Boy Scouts example, if they are unable to even to shout to each other to hear themselves what's happening in the patch next to themselves, one way to enable communication is to bring them together so they can share word information with each other and then go and do the tasks that are updated. So that's the idea that I'm looking for my work. This is when you have deployed the vehicles, you schedule a rendezvous point for them to go and meet together and then disperse again. This here is a diagram that is showing levels of autonomy, which is quite relevant, relevant in this case because different applications in different domains understand terms like autonomous or intelligent or adaptive and cognitive in a very different way. So in the area of underwater sensor networks, this is more the autonomy is the scale that is considered, and it's autonomous means basically that the vehicle is operating by itself without direct orders from an operator. Other ideas that I have looked at are from different fields that could bring some transferable solutions to the issue of resource management. And first of all, I looked at market-based control, which is work that Alex Charlish did for his multi-target radar.
Multifunction
radar. It's the idea is based on the economics idea of auctions. It's also a very popular choice for multi-robot systems. If you're having, for example, a robot that has to perform a task but is unable to do it by himself, he can auction this task to the other surrounding robots, and the ones that receive this signal, they can respond with a bid based on some utility function that comes down to a number, which is then compared between all the robots that responded. And the auction is won by the robot with the best utility function. So this is more or less how you designate tasks between the robots. However, one major issue for the application of this method in underwater environment is that it relies heavily on communication. And if you recall the example of Greg's, where only 60% of the messages went through, this means that all the auctions might have to be repeated constantly and to flood the system. Another thing that I was looking at is how to handle uncertainties, because often there are no when you deploy your vehicles, often you don't have maps for the ocean bottom, or you don't know what ocean current you're going to have during the operation, or how the vehicles are going to be scattered. So responding to those external events is quite important for such systems. And this is more in terms of managing goals. Once a goal has changed during the operation, if it needs to be cancelled or it needs to be amended. And some useful things that I found in this area was based on classical planning, but recently it has been applied with new relaxed assumptions into real-time strategy games, which is quite similar environment to what you can see with underwater networks. And the third aspect that I looked at was machine learning, and since my topic is looking into the intelligence of underwater sensor networks, machine learning is one aspect of intelligence which is introduced in robotic system. And I found some examples in neural networks and reinforced learning applied to underwater systems. But I have considered that my work is at a stage where I'm looking into the operations in general rather than building up on the intelligence. So this is more of a next level. Once I have the idea, this idea has to be tested somehow. So I had to go through the search of to choose a simulation tool to validate my results. And the three criteria that I have looked at while I was testing different tools was, are there enough libraries in the tool? My intention was not to start from scratch to start building a model in MATLAB, because this would be quite a generic view of the situation. I wanted to focus on specific application and solve specific problems. So the other criteria was the scope. Some tools, although they were focused on underwater research, they were not really looking at the whole system, but specific bits of it. And the third criteria was the community, how large was the community that was using the tool, because it's quite hard to solve a problem where there's very few people in the world that are using this tool. So first, I started with network protocol design, because I did a master in underwater communications. Then I started looking in network protocols, because they're quite closely linked, the two topics. So I looked into NS2, and then Desert and Sunset are two tools that are based on NS2. And they even have a model of the underwater channel, so you can have quite good representation of realistic system. However, this is just one aspect of the problem, just the networking, which is not the only issue why underwater networks are not deployed really. So this is why I excluded it based on the scope criteria. The other thing that I looked is multi-agent systems. JADE is the tool that Alex Charlish worked with for his thesis. And UNetSim is it's a multi-agent system that is that is more for underwater research. However, such systems would require building quite a lot of libraries just to start working on the issues I want to solve. So I exclude them as well. And in the end, I decided to use publish-subscribe architecture such as ROS, which is quite popular in robotics. Alan is working with ROS. He's using the manipulation of his robot arm with ROS. And MOS-IVP, which is my choice as a tool for the PhD, is quite similar to ROS in terms of how the tool is built, but it's more it has a lot of modules that are relevant to underwater robotics, and it has been deployed on quite a lot of vehicles already. So how this publish-subscribe architecture works is that you have a master node where all the applications are subscribing or they're dumping all their variables there, and you can other applications can subscribe to those variables to use them as their input, and then they publish their output back to the master node. So that's basically how it works. So you have to, when building a new application with new functionality, you have to connect it to all the others and get the inputs and push back the output. And the unique bit about MOS-IVP that I mentioned is the IVP Helm, which is solving if you have multiple behaviors working simultaneously on a vehicle, it is solving which one to get priority. For example, you can have a vehicle that goal is to go from point A to B to C, but at the same time it needs to stay at certain depth, and at the same time you want to avoid obstacles. So, so if you have an obstacle between A and B, this solver is going to decide what route to take and which behavior to take priority over the rest. The work I have done in terms of simulations in MOS is adding new functionalities that are relevant to mine countermeasure operations. I showed you one of the examples from the deployed networks where the common scenario is to have one search vehicle and one vehicle that is going after the targets that have been located. So I have simulated this scenario enables a vehicle to follow a lawn mower truck and then send the locations to the other vehicle to examine them. And right, so far I have designed a research strategy that is tackling the underwater communication limitations, which is the establishing rendezvous points for all the vehicles. The other thing is I have selected a test bed for the further simulations, and I have already developed some realistic mine countermeasure operation features. And what I would like to do further is to simulate the synchronous rendezvous scenarios, to introduce some external events which is more bordering with goal management. And another thing that's relevant here is building a utility function to optimize on certain parameters, for example, the area coverage. And another thing is to introduce a surface vehicle and to compare a rendezvous point between a surface vehicle and an underwater vehicle compared to a rendezvous between only underwater vehicles. And ultimately, I would like to measure the gains and losses for this idea of synchronous rendezvous. Thank you.